At 3,000 meters of water depth, standard anchoring is physically impossible. There is no practical way to secure a vessel of this scale to the seafloor using traditional chains or cables. This wireframe defines the GF12000 envelope, 230 meters long, 38 meters wide. It supports a 22,000 metric ton variable deck load, riser, drill pipe, cement, and fuel. The objective: lower a marine riser 10,000 feet, maintaining a perfectly vertical connection to the subsea wellhead. This creates a central engineering paradox. The vessel must exert constant force to hold its geographic position, while simultaneously preventing its own surface motion from reaching the submerged drill string. The GF12000 operates as a dynamically positioned power plant, a specialized machine engineered specifically to isolate and protect a stationary point on the seafloor. The vessel manages its stability by actively manipulating its draft. During transit between drilling locations, the hull rides high and light at a draft of 9.5 meters. To prepare for drilling, the crew floods ballast tanks low in the hull, pushing the vessel down to an 11-meter operating draft. This transition adds 11,500 metric tons of ballast water, bringing total displacement to 77,000 metric tons. A deeper draft lowers the center of buoyancy relative to surface wave action. This improves the metacentric behavior of the hull, allowing it to safely support the massive topside loads required for drilling. At the center of the vessel, a 24.8 by 12.8 meter open shaft, the moon pool, passes directly through the hull to provide a path for the drill string. Large hull openings are susceptible to piston mode resonance, where trapped water sloshes violently during wave action. Internal wave damping plates act as baffles to break up these resonant water columns. Draft and internal hull geometry are actively managed variables, used to transform a transit vessel into a stable, stationary drilling platform. This underwater view shows the physical muscle behind the dynamic station-keeping system: 6 fully retractable, azimuthing thrusters. These units produce a combined 33 megawatts of power. Because each pod rotates 360 degrees, they can vector thrust in any direction to nullify environmental forces without turning the ship's hull. Under the DP3 rating, the vessel's systems are physically and electrically segregated. No single fault, including a fire or flood in a localized compartment, is permitted to cause a loss of position. This mechanical power is only effective if the control system maintains an absolute understanding of the vessel's geographic coordinates. 4 sensor arrays feed this system: dual HIPAP, differential GPS, motion reference units, and wind sensors. A Coleman filter cross-checks streams in real time. If a sensor suffers signal loss, the system rejects the outlier, calculating thrust on validated data. Dynamic positioning relies on this algorithmic data rejection to maintain station-keeping integrity in changing environments. The vessel generates 42 megawatts of power using 6 Wärtsilä engines. To meet DP3 requirements, these 6 engines are split between 3 separate rooms. A60 fire-rated bulkheads ensure a catastrophic event in one zone cannot spread. If one room is lost, the power management system commands the remaining engines to increase output, preserving thrust. The power is distributed at 11 kilovolts. Generating at high voltage allows the ship to move massive loads while keeping physical cable sizes and electrical current manageable. Distributing 11 kilovolts carries high risk. An unmitigated ground fault could draw enough current to cause arc flashes and destroy critical distribution equipment. To mitigate this, neutral earthing transformers and current-limiting resistors are integrated into the grid. These components cap ground fault spikes at a safe maximum value. The vessel's architecture uses these spatial boundaries and electrical limiters to permanently quarantine localized disasters. In the derrick, the drill string forms a rigid link between the seafloor and the moving ship. This is the primary point of friction between ocean dynamics and drilling stability. The active Heave drawworks manages this connection. It uses high-response AC motors to spool and unspool the drilling line at extreme speeds. The drawworks reels cable in exact antiphase to the hull's heave, creating a flat, zero-motion line for the drill bit. During braking, the AC motors function as generators, converting the descending string's kinetic energy into electricity that returns to the ship's grid. While the drawwork stabilizes the drill string, the marine riser must also be tensioned independently of the vessel's motion. Because a rigid connection would fail under wave loads, the riser is held by pneumatic tensioners. Accumulator pressure vessels charged to 207 bar act as an air spring. The system allows up to 50 feet of piston stroke, absorbing vessel heave while maintaining constant upward tension on the marine riser. This riser terminates at the blowout preventer stack on the seafloor, a 15,000 psi rated tower of 7 independent rams. Multiplex digital control lines provide redundant paths to trigger these subsea rams. At the manifold, glycol injection is used to prevent gas hydrates, which could freeze while control lines shut. These systems, from algorithmic drawworks payout to kinetic riser tensioners, collaborate to prevent the kinetic energy of the ocean from reaching the subsea wellhead. The ultimate threat to this architecture is a total failure of the 11 kilovolt busbar, resulting in a full vessel blackout. The power management system handles this through fast blackout recovery logic, which automatically sequences the restart of generators and critical systems. An isolated 1700 kilowatt emergency generator starts immediately to restore power to life safety and navigation equipment. This emergency generator is sized only for critical loads, such as steering and communications. It cannot support drilling or propulsion. The fire and gas system utilizes an analog addressable architecture to remain functional and precise during emergencies. By placing LEL and H2S sensors directly at the mud pits and shaker rooms, the system can pinpoint the exact source of toxic gas breakout in real time. This technical illustration shows the final backup for internal communication, sound-powered telephones. The mechanical diaphragm uses the sound energy of the human voice to generate its own microcurrent. This system requires no external power. It relies on fundamental physical laws to maintain communication when all digital and electrical grids have failed. Through managed displacement, strict spatial segregation, and active heave compensation, they function as an integrated survival loop. The GF12000 functions as a highly segregated, actively compensating engine. Every system is designed to synchronize geometry and physics to isolate a fixed coordinate within a volatile ocean environment.